Next in our series of lectures on remote sensing, we're going to start talking about various sensor options. So we're going to limit our discussion to passive optical sensors because that's what most people use. There are more sophisticated sensors out there, but they're really targeted toward much more narrowly defined applications. So after a general introduction to how satellites are designed and what kind of considerations go into that design, we'll talk about the most often used satellites, the multispectral moderate resolution sensors like Landsat and Sentinel 2. We'll talk about multispectral low resolution sensors, most commonly MODIS. And then we'll talk about the class of high spatial resolution sensors. So those are things like Iconos, QuickBird, and WorldView. And then we'll briefly talk about the constellation satellite approach that Planet Labs and similar organizations pursue. So we've talked about airborne sensors and their advantages. So they can be tailored to the needs of particular projects. You can send them out when and where you need them. There are a variety of sensors that can be flown in them that are available to collect data, and in general, a greater variety of sensor types because it takes a while for new sensor technologies to make the leap from airborne configuration to spaceborne configuration. You can adjust your spatial resolution just by modifying your flight altitude, whereas with a satellite you're locked in at whatever the satellite's altitude is. Flight altitude can also be used to circumvent weather issues, so you can fly below clouds if you need to. You can extend your mission operations until the observations you need are made. This is important in data collections of things like LiDAR, where you may not be able to collect all the data you need on the first day due to, for instance, cloudiness or rain. So you're able to some extent, to the extent that your wallet can handle it, fly multiple days and sit on the ground until you get the conditions you want. And the temporal resolution is flexible. That is, if you need data every day or every week or every month, you can get it, whereas with a satellite you are locked in to a certain temporal resolution based on the orbit. The advantages of satellite-borne sensors are an unrestricted ability to cover the Earth's surface. For instance, Brazil is very touchy about having people fly sensors over their country. And so the only way you can get that done is basically through intergovernmental negotiation or the private permitting process that they have, which is difficult to get through. Essentially, you have to hire a Brazilian organization to do the flying for you. Similarly, in China, I have done some LiDAR data collection over China, and they wouldn't let me have my data. They would let me have numeric summaries of small parts of my data, but they wouldn't let me have the rest of it, and I had to have a Chinese collaborator do the analysis on that data. The advantages of satellite-borne sensors: the collections are standard and multiple dates are easily compared. So they're always going to be at the same time of day. They're always going to be, within a reasonable margin at the same spot on the surface of the Earth. For most sensors, you're looking at the same sun illumination conditions every time. So that takes out a lot of the variability in analysis, and long-term archives are generally available. But it's at the cost of constrained flexibility. You might say, wow, there's a flood somewhere, and I'd really like to be able to pick that up with Landsat to help in first responders. Well, if it's going to be 16 days to get there, it's going to be 16 days. You're going to have to rely on something else. The nice thing about multispectral spaceborne sensors is the sensors are tuned for a wide range of problems. There are science teams, they have multiple interests represented on the science team, and each portion of the science team works out what their requirements are for their applications, and then the engineers are sent off to figure out how they can come up with a single sensor that's responsive to all of those applications. The problem is that it's unlikely that a perfect sensor or perfect sensor configuration is going to exist for an individual problem because we're trying to address multiple questions, and that always requires compromise. So while you could have one sensor that could provide high spatial resolution, spectral resolution, or temporal resolution, providing all of these in a single sensor would be prohibitively expensive. You can see pretty quickly that if you're collecting a large number of high resolution pixels with many bands and trying to do that, say every day, then you're going to run into limitations. Number one, on the hardware, because you're going to require a lot of pixels in your, for instance, your push broom sensor. But also, one of the main limitations for these missions is just the amount of data that one can download from one of these systems. There's simply no way to get certain amounts of data down, and you're competing actually with other missions because they all use an infrastructure that's responsible for collecting data from satellites and then moving it down to satellite dishes on Earth. So to some extent, you're constrained by the existing set of sensors that are out there. So sensors can be classified on the basis of trade-offs in their spectral, spatial, and temporal resolution that result from targeting particular sets of applications. But many of the most interesting uses of remote sensing come when instruments designed for one purpose were applied to another, or when multiple sensors are used to complement each other. So a specific example that I was involved in involved the Hyde Park fire, where we had Landsat images from just after the fire, which was a stroke of luck. But we also had higher resolution sensors that we could use in a photo interpretive capability. So we could actually go in there, figure out, lay out plots in a strandified random and clustered manner, photo interpret each one of those plots to say what percentage of the plot was burned, then use that data along with Landsat data to come up with a map of the percent burned for the entire Landsat image. So current capabilities of Earth observing satellites, these tend to fall out into discrete groups, again, because of what the kind of applications there are for them. High spatial resolution domain, these days it's about 0.3 meters to 4 meters. They keep pushing the technology for high spatial resolution sensors, and so that's gradually gone down from about a meter at the beginning of the high spatial resolution era to about, well, right now the highest spatial resolution sensor is about a quarter of a meter, but the Defense Department doesn't allow you to sell data with that high resolution. So I believe it's resampled to 0.3 meters. Doesn't seem like much of a difference, but apparently it's important to them. There's this sort of moderate spatial resolution of 10 to 30 meters, and that's going to be your Landsat and Sentinel class systems, which those are the ones we'll talk about the most. That tends to be a good scale for general land use mapping when you're looking at, say, a single date or a small number of dates. 100 to 500 meters, that's much more useful for systems that are going to map the Earth, once a day or even a few times a day, up to, once a week, for instance. And then finally, we have a coarse scale system that are between like 1 kilometer and 8 kilometer. And these are generally systems that are meant to collect data once a day to many times a day. So meteorological satellites, for instance, are generally around 8 kilometer spatial resolution, and they're collecting data every 15 minutes or an hour. Temporal resolution, you might have something like those meteorological satellites that are giving you images every 15 to 30 minutes. You might have something like the MODIS system that does daily data collections. You might have something like, we'll talk briefly about the now defunct Rapid Eye system that gave you 5-day temporal resolution. And then bi-monthly, twice a month, things like Landsat generally cover the Earth, every 16 days. Finally, we have 3 spectral domains. One of them is panchromatic. Well, that's just one band. The other is, or another, is multispectral, so say 2 to 6 or maybe 2 to 8 bands now. And finally, you have hyperspectral domains, so that's between 10 and 100 bands. So that's the general introduction to what kind of sensors are out there. We're now going to start talking about the multispectral moderate resolution sensors. So Landsat is the sensor that immediately comes to mind when you're talking about this kind of sensor. So it's the longest, it's the most comprehensive record of the Earth condition ever assembled in the Eros Landsat archive, which includes almost all of the images that have been collected with Landsat. There are more than 6 million images, which is 171 billion square kilometers, that were collected from 1972 to the present, and they span the globe. Now, they don't very often do water collections, and they don't very often do Antarctic and Arctic collections, because once you get up to the poles, the lighting conditions become poor. There has been an attempt to do an Antarctic mosaic that was done with Landsat. All Landsat images are available to anyone at 0 cost. It used to be that you had to pay for these things and then sign a pledge that said you wouldn't share them with anyone else. And that worked out really well. People definitely always adhere to the not sharing pledge. So each year, 5 million images are distributed to users in over 180 nations and territories. And it basically all starts with Landsat. Early land viewing satellites were designed for broad-scale meteorological observation, so basically looking at clouds and cloud distribution patterns. Landsat, which stands for Land Satellite, was the first one tailored specifically for systematic observations of the Earth's surface. It was designed in the late 60s, launched in 1972 with broad scientific support. It was just a big U.S. investment. There were no guarantees that the program would succeed, and In fact, it wasn't thought that this was going to be what wound up being so far almost 50-year program. Um, and the experience provided the operational knowledge and the knowledge of feasibility that then spurred worldwide development of similar remote sensing systems. Um, so the Landsat system consists of spaceborne sensors that observe the Earth and then transmit information to ground stations that receive and process data for dissemination to users. There have been 8 Landsat satellites. There's a 9th one that's supposed to be flown in December of this year. And these were really, there were sort of 2 sources of motivation. One was the views that were gotten from meteorological scientists, which started making it very clear that the Earth didn't look like the way that they had thought about it. And the other would be the Apollo mission photographs, which were, it's hard to imagine now, but were really stunning, had a real effect on public knowledge. This was about the time that the environmental movement was getting going, and the notion that the Earth was one big system is one that was readily captured in those few images, those few color images that came from the Apollo missions. So Landsat 1 was originally referred to ERTS-1, the Earth Resources Technology Satellite, but apparently someone in public relations said, listen, let's call it something a little catchier, so it became Landsat, and it really was an experiment to test the feasibility of collecting multispectral Earth observation data from just an unmanned satellite platform. So again, they had no idea what this was going to become. There have been a number of sensors that have been on the Landsat series of satellites. Until Landsat 8, those were the return beam Vidicon, which was basically a TV camera pointed at the Earth. That's the sensor that they thought was going to be the main sensor. So this would be on like Landsat 1. But it turned out that the multispectral scanner, which is much more like a system that we would think of in terms of a scanning remote sensing system, was the one that people found very popular. And then later on Landsat 4, the thematic mapper, which is sort of an improved version of the multispectral scanner, was launched. So the most popular instrument in the early days was the multispectral scanner. Later you had the thematic mapper. Each of these sensors collated data over a swath width of about 185 kilometers, with a full scene being defined as 185 kilometers by 185 kilometers. Note that these are cross-track scanning systems, so there really is no scene height. The scene, there's a swath width that's a real value because it's determined by the mechanics, but you can cut off a Landsat scene anywhere you want. But it just so happens that people like square grids, and so the full scene is defined as 185 by 185 kilometers. The current system now on Landsat 8 and to be launched on Landsat 9 is the operational land imager, which is an improved version of the thematic mapper. It adds a few bands, and it is a push broom system. If you recall, we talked about the problems that Landsat 7 had with a scanning system, and so it was decided that for Landsat 8 and going forward, you would have push broom systems that wouldn't be reliant upon on that extra mechanical devices that you need for an across-track scanner. All Landsat satellites, we've talked about this, they're placed in a near-polar sun-synchronous orbits. The first 3 satellites were at altitudes around 900 kilometers, and therefore they have revisit periods of 18 days, while the latter satellites all are about 700 kilometers and have revisit periods of 6 days. And all the Landsat satellites have equator crossing times in the morning so that you can have optimal illumination conditions. That difference between 18 days and 16 days results in a different number of paths. So the paths are the north-south distribution of the satellite images. The rows are, the paths are the east-west distribution of sensors. So there's a path that crosses at, say, 0 degrees west, and then another path that crosses at whatever that would be, 15 degrees west, then another at 30 degrees west. There are also rows, and those follow latitudes. So again, coarsely, they're, one at the equator, one 185 kilometers above the equator, etc., etc. So paths are the columns, rows are the rows. The important thing to know is that subsequent rows, so as you're going north-south, are sampled continuously. It's a scanner success there. It's not frame capture. And then adjacent paths are sampled 1 day later. So that means that you have continuous weather conditions north-south. So if you've got, if you're socked in by clouds at one particular path row combination, you're probably going to be socked in by clouds at the next further south path row combination. However, the next adjacent path is sampled 1 day later. And so by then, weather conditions may have changed. So it just makes it very different when you're doing mosaicing, whether you're working north-south or east-west. To give you an idea of the kinds of bands that are in each one of these sensors, MSS has 5 bands. The bands are labeled 4, 5, 6, 7, 8. And the reason they're labeled that way is that the reverse beam Vidicon is given the numbers 1, 2, and 3. It's just a legacy issue. It kind of represents a strange way of thinking about the whole problem, but a lot of these things you just have to shrug your shoulders and say, well, they were the first ones to do it, so they're allowed to screw up some. So we've got a green band, a red band, a near-infrared band, a second near-infrared band, and then a thermal band. The optical reflective bands are about 79 by 79 meters. So that's for bands 4 to 7. And the thermal band is 240 by 240 meters. And again, that's just because of sensor technology. There's less energy at that portion of the spectrum, so you need larger pixels to collect it. It's only 6-bit values, so you can only represent values of 0 to 63 or 64 levels of grayscale, which is a real problem when working with this data when you want to do things like forest classification, because you know that a lot of other things are as dark as forests, and it would be a real help to have those extra 2 bits that you get in Landsat 7. The MSS flew on 5 Landsats, so it flew on the 18-day Landsat 1, 2, and 3 sensor satellites, and then on two 16-day Landsats 4 and 5. Again, altitude about 919 kilometers and a swath width of about 185 kilometers. That 18 to 16 day coverage or temporal resolution is important because if you think about it, if you've got an 8-day temporal resolution, it means that you have more paths than you do with a 16-day. And so as a consequence, the first Landsat's paths don't line up precisely with the second set of Landsat paths, the one we used from Landsat 4 through today. So as a consequence, you get the problem of having to mosaic early MSS data together in order to have a tile that includes both the Landsat, say a Landsat 4 TM image and a Landsat, 3 MSS image, and it becomes a tremendous pain in the neck. Fortunately, if you're interested in that kind of work, there was a group that sat down and actually worked out nice mosaics that are all targeted to the year, like, I want to say it's like 75, 80, 85, 90 maybe, and came up for the United States and Mexico with stacks of images where they found the best possible images to overlap with the second set of 16-day repeat paths. When we go to Landsat 4 and 5, the thematic mappers on these systems. So what changes have we made here? Well, we've added in blue as band 1, and we've taken out that second near infrared, and we've put in 2 shortwave infrared bands that are labeled, strangely, 5 and 7. I don't know if I've gone over this, but I find it a funny story, so you're going to hear it again. Which is, originally they thought that they could put 6 bands on Landsat 4 on the thematic mapper. And so they developed all of their documentation with 6 bands in mind. And then someone realized, oh wait, we could squeeze a 7th band in here. It would be another mid-infrared band. And so they were left with a choice, one of which was to rewrite all of the manuals to make the new mid-infrared band, band 6, and move the existing band 6, which was thermal infrared, to band 7. And that way, there'd be all the spectral values would be in order. But this is, back in the type of typewriters. So nobody wanted to have to go back and do all that editing and make sure that they got every single example. And so what they decided to do was just to make the second mid-infrared band, band 7. And so then they could just type it at the bottom of tables and not have to worry about reformatting the original documentation, which I find to be a clever solution. It's probably the one I would have voted for. Thematic mapper has a dramatic increase in spatial resolution, or a dramatic improvement in spatial resolution. So there are 30 by 30 meter bands for bands 1 to 5 and 7. So visible, near, and mid-infrared, and then 120 by 120 meters for band 6, the thermal band. These are 8-bit values, so that's an incredible improvement. All of the thematic mapper data was collected with on 6-day orbits. Landsat 7 was very much like, well, Landsat 6 was very much like Landsat 5 in terms of having a thematic mapper. It was called the enhanced thematic mapper, which meant, I think, that it had just that it had better spatial resolution. The reason I don't know the answer to that question is that Landsat 6 immediately took a dive in the ocean and was never operational. So on Landsat 7, it's called the Enhanced Thematic Mapper Plus is the sensor on it. And the reason it has like two, it has both enhanced and plus, is because you have this missing Landsat 6. Landsat 7 adds an 8th band. That's a 15 by 15 meter panchromatic band, and that is used to help increase the spatial resolution that you can achieve with the other bands. And we'll talk about that when we talk about pan sharpening with high spatial resolution data. The spatial resolution on the thermal band is 60 by 60 meters. So that's the other big difference. And of course, Landsat 7 had the problem with the scan line corrector, so it only operated for 4 years before it seized up and stopped giving the high quality data. Fortunately, it's really hard to figure out how long satellites are going to last. So Landsat 5, all of these systems are, they're constructed with a budget assumption that they're going to last for 5 years. Landsat 5 lasted for 20 years, and you never can tell. You get a random cosmic ray, and all of a sudden, your system is faulty on day 1, or you luck out and suddenly you get 20 years on your satellite. You can't really tell. So this is a comparison of the operational land imager that is on Landsat 8 and the TIRS, which is the thermal infrared sensor on Landsat 8, with the earlier, this is Landsat 7 data. So if you look, first of all, they reorganized the order of the bands, so that's nice. So if you look, the first band now is a coastal aerosol band, so that helps you in your coastal zone observations. It's going to have way more Rayleigh scattering, but it's going to help you correct for the Rayleigh scattering in the blue band. Blue band's the same, green band's the same, red band's the same. Near infrared is the same. SWIR 1 and SWIR 2 are the same, only now they're in the correct order. They're band 6 and 7. Band 8 is the panchromatic band, which in Landsat 7 included both the green, red, and near infrared portions of the spectrum. Now it only includes the green and red portions of the spectrum. Band 9 is a cirrus band. It's kind of sitting out there all alone, and its job is to detect high altitude cirrus clouds that might otherwise contaminate the spectral signatures that you would get from the other bands. Band 10 and band 11 are two thermal bands, each one at 100 meters, and each one having more or less adjacent portions of the spectrum. The reason why you have two is that you can do comparisons that allow you to correct for emissivity. They're called split window approaches to thermal data processing. And so having those two bands makes the thermal bands more useful than just having one. So the advantage of Landsat data, we have this synoptic view, which just means that it covers a nice chunk of the Earth at once. You know, that happens to be convenient. If you're dealing with, Colorado, then you're talking about maybe 40 images to cover the whole thing. That's not too bad, to be able to do that at a 30-meter spatial resolution. Obviously, it's got a digital format, so you can do quantitative processing and analysis. It kind of has the right spectral information content, particularly with the thematic mapper going forward. No one's really come up with another band that, gosh, you'd really like to have. The only thing that was added was that cirrus band for atmospheric correction, and that is an advantage. But no one said, oh, we really ought to be hitting this other part of the shortwave infrared. It's got a 16-day repeat cycle. When we get Landsat 9 up, we should have 8-day repeat cycles. And that's something that people have thought about for a long time, particularly for agricultural monitoring. It's relatively low cost. Both the sensor itself does not cost that much money, and doesn't cost anything now to download the data. It's a consistent scale and format, so dealing with one image is very much like dealing with any other image. It's applicable to multiple data problems, I'd say. That is, it's good for soil mapping, it's good for agricultural production mapping, it's good for forest age mapping. There's a heck of a lot that you can get done with one Landsat scene. And you do get nearly complete coverage of the Earth's surface, although there's no ocean coverage. I think at one time there was an attempt to get ocean coverage. There is coastal coverage, but I think that the actual deep ocean has maybe once been surveyed. The limitation is small scale of the data, that is coarse pixels. Cloud cover is a problem, but it's always going to be a problem with an optical sensor. And that 16-day cycle really is inadequate for many things. Like I was saying, we're looking forward to getting an 8-day cycle with Landsat 9. And just a little historical callback here. In '91, when I started my career, Landsat 5 seeds cost $4,500 per scene and could not be shared. And that was a lot of money. That's a lot of money now, but it was probably more like $10,000 in today's dollars in 1991. But as of 2011, all data is now archived and are free, as are things like MODIS. Okay, so now we're looking at ESA, the European Space Agency, and they have had a system or a suite of systems named the Sentinel systems. Sentinel-1 was SAR, Sentinel-3 is low resolution optical imaging and ocean altimetry. Sentinel-4 and 5 are atmospheric monitoring. And then Sentinel-2 was high resolution. I wouldn't call it high resolution, it's moderate resolution optical imaging. So there are two Sentinel-2s operating in a twin configuration. There are 13 bands in the visible, near infrared, and shortwave infrared. But not all of those bands are collected at all resolutions. There's 10-meter data, 20-meter data, and 60-meter data. It's a sun synchronous orbit at about 790 kilometers. So it's doing 14 plus 0.3 revolutions per day with the local time of crossing the equator at about 10:30. And the swath width is 290 kilometers, so a bit bigger than Landsat. It's systematic. It's all land and coastal services between -56 and +84 degrees latitude. It revisits every 5 days at the equator when you consider having 2 satellites, okay? And that's, you know, every 5 days you should get 100% coverage of the area it covers, unless you consider clouds, in which case it's going to be a longer revisit period. It can do lateral pointing, so you can shift the satellite off nadir in order to pick up areas adjacent to the current path. And so any point on Earth can be observed within 1 or 2 days, provided it's not cloudy. These are push broom sensors, and the lifetime is supposed to be 7¼ years, extendable to 12 years, but again, it's very, very difficult to know how long a system is going to last in space. So this gives you an idea of what bands and how they're distributed among the wavelengths and spatial resolution. At 60 meters, we have bands that are probably mostly going to be used for atmospheric correction. So we've got a blue band and near infrared band and a shortwave infrared band. At 20 meters, we have a series of bands there that are kind of red edge between red and near infrared band, and then 2 shortwave infrared bands. And then finally, at 10 meters, we have sort of a blue-green band, a green band, a red band, and a near-infrared band. And it's nice, they give you these nice diagrams where they've calculated out the revisit time over various parts of the Earth, and some are with 2 satellites. So considering cloud cover, so if you've got 2 satellites, then it's between 0 and 5 days. They're mostly going to be close to 5 days there for visit times. And then as you go further north, you get longer and longer periods between good observations. You might get, in England, you might be 85 days between a good coverage. And that is only a 15% cloud cover that they're determining as a cloud-free day. So put that in your tea and drink it.